This video covers Gauss's Law Part 2. In the next couple of examples, we're not looking at any new material. All we're doing is applying the stuff that we learned last time to new examples. This first situation says, a solid conducting sphere holds a 4 Coulomb charge. It is surrounded by a hollow conducting sphere that is neutral. So these pieces that are underlined are very important. Now the first part says, draw pluses and minuses to represent the charge distribution. So on our inner sphere, we have 4 coulombs of charge. Now, because it is a conducting sphere, that tells us that our charges are going to be on the outside surface of this sphere. So here we have my positive charges. So when the outer sphere is a conductor, the charge on the inner sphere will always attract the amount of charge equal to the outer sphere. So again, because it's neutral, I have 4 coulombs of charge on the inside. So I represented 4 charges. These 4 charges are positive, so they're going to be attracting 4 negative charges on the inside. Now, the outer ring is still neutral, but these charges have now rearranged themselves, and it's allowed to because it's a conductor. Now, we said that the outer sphere is still neutral. In order for it to still be neutral, or for us to represent that, we need to now show that we have 4 positive charges on the outer sphere. So, my outer sphere is still neutral, my inner sphere has those 4 coulombs. So, the charge on the outer surface of the outer sphere must add to the charge on the inner surface and equal to the total charge of the entire outer surface. Now, this is true in all situations, not just neutral surfaces. So now we're going to draw our electric field lines. Our electric field lines always go from positive to negative. Now, we know that inside of our conductor, at the very center, the very surface, we're not going to have any charge, right? Because all of our charge acts on the outer part. So I'm not going to show any electric field there. But here I will have an electric field, and my electric field will go outwards. So it'll go from positive to negative, positive to negative, positive to negative, and positive to negative. Again, the outer shell is also a conductor. So inside, between these negative and positives, between these negatives and these positives, I still don't have an electric field. And then outside of that, I will also have an electric field. So again, these positives are going to go outward. Will go outward at all points. Now for part C, it says, if you are standing just outside each sphere and look inward, what charge will you see? This is imagining our Gaussian surfaces. So let's say that we create a Gaussian surface here. Then if you stand at that point and look in, you're going to see a positive plus charge. Or 4 coulombs. If I stand outside even further, I'm still going to see 4 coulombs. Because again, the outer sphere is still neutral, so the total charge enclosed is still 4 coulombs. So in this example, we're asked to graph the electric field as you move outward from the center. So these lines right here represent the different ways my electric field can decrease. We know that the relationship between distance is 1 over r squared, so these are 1 over r squared lines. Okay, so starting with the center, we know that we're not going to have any electric field right at the middle because we have no electric field inside of our conductor. At this point where we have our red line, we're going to have a charge enclosed of 4 coulombs. So we're going to jump up for convenience to this line right here, the 4th one. Again, as we move from this inner sphere to the outer sphere, we do have electric field lines like we saw and we drew in the previous examples. Now, in between this negative and positive charge, because again, it's a conductor, we're still not going to have an electric field. So again, it jumps back down to 0. And then outside of the conductor, outside here of this red line, we are going to have an electric field. But again, all of it's being taken from the center. So our electric field is going to decrease. So it doesn't have the strength that it did between the positives and negative earlier. So it's going to follow this line here. Okay. So to connect everything, again, 0 electric field in the center. It jumps up to its highest strength, decreases again back to 0, jumps up after it's exited that conductor, and then travels outward. In the second example, we're applying the same ideas, but now we're looking at a solid insulating sphere that holds a 2 coulomb charge distributed uniformly through its volume, so it's telling us it's an insulator. It is surrounded by a hollow conducting sphere with a -6 coulomb charge. So we want to start by placing our charges. We have 2 positive charges placed on the center, again, evenly distributed. These 2 positive charges are going to attract a negative charge and another negative charge. So it'll attract the same amount that it has. And what it cannot attract, it will be distributed on the outside of this sphere. So we have 2 negative charges that are being attracted to it. And then we have the remainder of the charges, which are -4 on the outermost surface. Again, because the outside sphere is still a conductor, we still have no charges placed on the inner part of the outer sphere. So we saw these examples in our previous video. Because we have an insulator, at the very center, we're still going to have an electric field of 0, but as we move outwards, we're going to start increasing linearly. Once we leave this sphere, our electric field will start to decrease with the distance. Then we're going to reach this part of our surface. Again, from here to the end, we have no electric field because we have no charges here. Again, you can also draw the electric field, which is from positive to negative, and then here it will be negative. So that means when we get to the outer part, outside of the outer sphere, then our electric field will be negative. So we see this jump down, and then again, the magnitude of that electric field starts to decrease with the distance. In this example, we have a solid insulating sphere with a 4 coulomb charge, uniformly distributed throughout its volume, and it is surrounded by a hollow insulating sphere with a uniform -7 coulomb charge. So again, we have 4 positive charges being evenly distributed, and these -7 coulomb charges are going to also be evenly distributed. So these don't exactly gather up on the edge like they do with conductors. 1, 2, 3, 4, 5, 6, 7. Okay, imagine that's evenly distributed. Now we know from our previous video that inside our electric field, inside this very center, our electric field will still be equal to 0, but then it starts to increase linearly as we move away. So I'm going to increase until I hit 4. Afterwards, we're going to start decreasing with distance. Now for this one, while we're going through the blue section right here, imagine a Gaussian surface starting at this point and increasing as we move outwards. So as our Gaussian surface gets larger and larger, so let's say it starts out around here, and then it gets slightly larger and slightly larger, what we're doing is encompassing or including more and more negative charge. So as we include more and more negative charge, the overall or net charge starts to decrease. And at a certain point, it will actually be 0. So again, our net charge is going to start decreasing. It'll actually be 0 at some point. And then once we get to the outer edge, our net charged enclosed is going to be a -3. So this is going to go down all the way to -3. So increases linearly, decreases, and then starts decreasing as we have an additional charge being enclosed by our surface. So this would be a +4 if we stood outside this red one, and this would be a -3 if we stood outside the blue sphere. And then again, as we move away from both of these spheres, we just follow this path. In this example, I need you to update your notes. So instead of, we are still going to have a solid conducting sphere, but instead of -4 coulomb charge, I want you to change that to a -3 coulomb charge. It is surrounded by a hollow insulating sphere with a, instead of 2 coulombs, I want you to change that to 6 coulombs. And this charge is distributed evenly throughout its volume. So again, putting our 3 charges at the center, because it's a conductor, they're going to be on the outermost surface. We have no electric field inside of a conductor. As we move away from our conductor, we start to have a decrease in electric field, but this is negative because our charge is negative. So again, a decrease. As we move through an insulator, we have this linear graph. Again, because the outer charge is positive, the more and more positive charge we get, the closer and closer we get to an overall net positive charge, which will be a net 3 coulombs. So here, we'll have 3 as our electric field. And then again, we decrease as we move away from it. So if we were to stand outside between the gap of these 2 spheres, you would see a -3 charge. And if you were to stand outside both of these spheres, you would have a +3 charge. In this example, we're getting a little bit more quantitative. It says a solid conducting sphere holds a positive Q charge. It is surrounded by a hollow conducting sphere that is neutral. So again, same example that we saw before. But now we don't have such convenient numbers. Hollow conducting sphere that is neutral. So we want to figure out what our electric field is at A. Again, we can still use Gauss's law. And again, you should be familiar with this derivation by now. The charge enclosed in this case will be 0. But we'll see that at the end. Again, for part A, our charge enclosed would be 0, so our electric field is also 0. And again at B, because this is inside of a conductor, we still have no electric field. We still have not enclosed any charge. At point C, we have now enclosed all of the charge on the inner sphere, so our charge enclosed is +Q. The radius is going to be the radius of the inner sphere, which in this case is A. We can simplify this to KQ over A squared. Again, this will have some value. We're going to go up. It'll have a positive value. Now at point D, we're outside of our surface, so our charge enclosed does not change. We still have a +Q charge. But our radius is now the radius of our new Gaussian surface, which is not A or B, but we'll call just R. Really, this should be KQ. It doesn't really matter, but it's okay. Where R is between A and B. Again, we know that the strength of that electric field is going to be less than what it was at point C. At point E, we have now entered our other outside conducting sphere. So now the charged enclosed is now 0 again. So for charge enclosed, I'm going to say that we have a +Q on the red sphere, a -Q on the blue sphere. Our radius would be B, but that just gives me 0 as my electric field. Again, because point F is inside of a conductor where we have no electric field, then I can say that my electric field or my charged enclosed would be still 0. And again, you can always prove that with Gauss's law. It is important that you go through the process of proving it, because you can get a lot of credit just by showing your math and proving, not just saying, oh, inside of a conductor it's 0, but actually showing that. Where in this case, R is in between B and C. Again, now when we get all the way to the outside, our charged enclosed is the Q of our innermost sphere and the 0 charge, or the 0 net charge, on our outer sphere, which gives me a charge of Q. But now my R is C, and my electric field is proved by this. So again, 0, some electric field, decrease, 0, and then continuation of that decrease. Again, the continuation of that decrease, like we've seen in several examples now for part H. Now this example is probably the hardest of them all. It says that a solid insulating sphere has a uniform negative charge. It is surrounded by a hollow conducting sphere with a positive 2 charge. So we want to solve for the electric field at A. Again, we know that it's 0. You can prove that our charged enclosed is 0. Therefore, our electric field will also be 0. And we've seen that derivation. Now, point B is not the same as we've had it before. Again, here we have a solid insulating sphere with a negative Q charge. So now we do have an electric field at point B. And the electric field at point B is still the charge enclosed over 4 pi r squared epsilon naught. But now we need to figure out what's our charged enclosed. So we said that our density of our sphere is going to be equal to the density of the actual sphere. So we'll change this first S to an R. So the density of our Gaussian surface is equal to the density of the actual sphere. So that means the charge on the surface is equal over your charge over the volume of the surface is equal to the charge on the surface versus the volume of that surface. Again, these are real or actual. These are Gaussian. Again, our volume, so Q enclosed is our charge over Gaussian surface. Our volume will be 4 over 3 pi r cubed because we are talking about a sphere. The actual charge on this sphere is negative Q, and the actual volume will be 4 over 3 pi capital R cubed. Pi's will cancel out, 4/3 will cancel out, and you're left with a charged enclosed of a negative Q over R cubed. We should put little r cubed up on top. So again, where we see Q enclosed, we're now going to be putting in negative Q R cubed over R cubed over 4 pi R squared epsilon naught. And you can make some simplification here. These R's will cancel, and you're left with negative Q over 4 pi, there's an r on top, r cubed down at the bottom, epsilon naught. And then to be very specific for this particular situation, our capital R, actually our lowercase r is going to be just the r that of our Gaussian surface, so whatever the radius is from A to B. And then capital R will be the actual radius of the insulated sphere, which in this case is A, and we're going to cube it. And this is our electric field at point B. So we know it's going to be some negative value. So looking for the electric field at point C, we know that at point C, our radius of our Gaussian surface is going to be equal to A. The actual radius of the surface is now also equal to A. So we can plug all of that in. And we can see that our A's will cancel. And you're left with the same equation that we've gotten in previous problems for our electric field. Again, our electric field at this point is now the greatest it's been because we have the most charge enclosed. So we saw again that linear increase in our electric field. As we move from C to E, we are going to see that decrease in our electric field. From E, F, and G, we have a conductor. So again, we know that we have no electric field at those points. And then as we go from G to H, then we jump back up to where we left off, and we start to continuously decrease from there. Now, for the very last example, I want you to complete that with numbers, and then we'll check our answers in class.